Welcome back to the last lecture of this series. We will talk about reasoning ability of transformer by this phenomenon-driven approach. Have you ever seen a TV series called Westworld? It's basically a story about robot or AI agent with human being. And in this Westworld, people can tune different parameters to change the characteristics of this AI, human-like AI, like humility or humor and so on, maybe IQ, EQ, and so on. And now we know that transformer-based artificial general intelligence seems very powerful. Can we find some hyperparameters that we can tune it to change its some characteristics? And we will focus on memorization and reasoning ability. The question now, what is memorization and reasoning? How to define this? Actually, it's not an easy task to do this. So we can define it by some examples, and we will use a very famous example. We know that Zhi-Qin, he recorded the data of planet through his whole life. That is called memorization the data. And his student, Kepler, realized there are three laws inside this data. Now we call it Kepler's laws. And we can understand the law of planet motion. And Newton, he summarized these rules and proposed this universal gravity law, and also the second Newton's law, and so on. By this more reasoning, we can apply these rules to more scenarios and do more things. Now, if we inject this data into a neural network, the question is, how will neural network to fit this data? By memorization without any generalization, or have one-step reasoning just like Kepler's, and we can apply it to more planet data. Or we can do it like Newton to have more reasoning, to propose more basic rules and apply it in many fields. Definitely, this is also a very complicated task. The model and the data are both very complex. And can we study one by one? Yes, we can study it one by one by designing a simple task to study the neural networks. So now, I will ask you to do a very simple task. This may be a math task for primary student. You should remember these equations, and we will do test. Okay. Now, how many numbers pairs can you remember? It's not an easy task. Let's analyze this data set. One way to remember these data points is to take a photo, and we don't need to do anything. And once you ask me anything, I just look up the picture and tell you the answer I have taken photo on. But definitely, there is no generalization for this. And if we don't want to remember all so many data pairs, we should have looked more carefully into the rules underlying these data pairs. We found that actually there are 16 functions. There are 4 primitive level function 1, 2, 3, 4. And this 4 elementary function can form 16 composite function. So instead, we can remember these 16 function relations. But even 16 function relation is still very difficult for us to remember. And we can dig into it more. And we found that there is a symmetry property. That is, the index 1 and 2, if we switch their position, the answer is the same. Similarly for other pairs. So this is a typo here. This should be 2, 3. So when we have this observation, now we only need to remember 10 data pairs or 10 functions. And if we dig more, we found that we only need to remember 4 elementary functions and use these 4 elementary functions to make composition. And finally, for any test, we can use these 4 elementary functions to do it. So from this right side to left side, the reasoning complexity gradually increase. And in the other side, on the other direction, the memory complexity definitely increase. So by this very simple example, we actually define the reasoning complexity very specifically, or memory complexity. And the question we want to ask is, how will large language model do if we ask the model to remember the data? And to answer this question, we will start from a very simple task, and we define it as an anchor function. The anchor function is a technique for those who are not able to run so expensive large language model task. We don't want to remember all the natural language in order to do just a very simple task. So we defined some tokens as anchor and other tokens as key. And all these tokens are just the integer number, and we we encoded by one hot vector followed by an embedding. Now we designate 1, 2, 3, 4 as a specific function. If a number encounters 1, you will plus 5. And encounters 2, you will plus 1. For 3, minus 2. For 4, minus 8. And these 4 tokens are only used as anchor. And other token will be used as keys from 5 to 100. So now we can construct data as follows. 21 encounters anchor 1, so you are plus 5. The result is 26. And it encounters number 2 indicates plus 1 operation. So the final target, final solution label is 27. Similarly, for any key, we will go through these anchors one by one until we get this target. So the data here actually is key, anchor, and target. And we will train models to predict targets. So for a network, we have this input and also the output for prediction. And now we can put in the data into transformer model. This key is the preceding anchor proceeding token of the anchor. And we can use next token prediction or use only last token prediction. That is, we calculate loss for the last anchor token. And we do the back propagation only based on this loss. Now, there are two kinds of generalization. One is data generalization. The combination of anchors is seen during the training, but the combination of key and anchor pair are not seen. The second generalization is called task generalization. 4 and 3, this pair is not seen during the training. In the next, we will only mask the pair 4 and 3 during the training. They will not be seen in the training data. And we found that it's quite easy to complete this data generalization without too much tuning of hyperparameters. However, for this task generalization, it is slightly difficult. And we want to ask, can the neural network learn the operation of 4 and 3, which are not seen during the training? The answer is we found that yes, it can. It can learn 4 and 3, the operation. And we want to ask what kind of mechanism it learned it. At least there are two possible mechanisms. One mechanism is called symmetry. We know that this addition or subtraction, they follow this symmetry property. The function of 1, 2 equals 2, 1, 2, 3 equals to 3 and 2. So once the neural network learns the function of 3 and 4, it can apply its operators to the function of 4 and 3. And for the second mechanism, that is, it can infer the single anchor's mapping and find that the anchor 3 indicates -2 operation, and 4 indicates -8 operation, and their composition should be -10. So now the question is, which mechanism, the neural network, we will adopt to fit the data? To understand which mechanism, we need to look into the circuit of transformer very carefully. Instead, we slightly change the task. Now, we slightly change the operation of 3 and 4. By the composition rule, it should be -10, but now we change it to -6. So the 4 and 3 is still an unseen composite anchor. And if these unseen anchors learns the operation of -6, we know it adopts this symmetric structure. But if it learns the solution of -10, we know it analyzes other 14 anchor pairs and realize it's highly possible that 3 indicates -2 and 4 indicates -8. And then it has this composition for 4 and 3 as -10. So which mechanism you believe the neural network learns? Now you only need to examine what's the solution of 4 and 3. And we will tune the hyperparameters. We focus on the initialization scale. We initialize neural network's parameter by a Gaussian distribution with 0 mean. And the hyperparameters we tune is not simply this variance, but a very specific parameter, we call it initialization rate, gamma here. And this D is the number of neurons of the input layer. And we will show this gamma is a very critical one. And now, usually very few people will tune this gamma, but tune this variance instead. Now let's take a look. And we know that if this gamma is large, indicate a small initialization. And if this gamma is small, this indicates a large initialization. And now let's take a look of this result. We compute the accuracy with respect to this inferential solution or symmetric solution. For large initialization, we know we can see that this green bar dominates, and this green bar indicates that the solution is highly consistent with the symmetric solution. So for large initialization here, the neural network use symmetric structure to fit in the data. And if we decrease the initialization or increase the initialization rate, we can see that the inferential solution dominates, meaning if we use inferential solution as a ground truth, the accuracy is very high. So if we increase, if we use large initialization, it tends to learn a symmetric solution, and use small initialization, it tends to learn this inferential solution. But if we look back to our analysis, there are not only 2 ways to learn this data, but 4 ways at least. Can we tune more carefully to let the neural network learn the data by each way? Yes, we can, but we slightly change the setup to remove this inference of this inferential solution of 3 and 4. So we have 16 computation functions, but we let 3 and 4 and 4 and 3 unseen during the training. So we only have 14 computation functions during the training. And similarly, we only tune the hyperparameters gamma here. Now let's take a look of the solution. So we will examine 2 accuracy. One is the CN anchors for these 14 trained anchor pairs, and the other is the solution for 3, 4, and 4 and 3. So if the initialization is very large or small rate, this blue curve is the accuracy of seeing the anchor pairs, and this red one is for the unseen anchors. So we can see for unseen anchors is very hard. Its accuracy is very low. And for these seen anchors, it continues increase if we decrease the initialization or increase this gamma. So in this case, both the seen anchors or unseen anchors, its accuracy is low, so we can regard it as a memorized data regime, because the training data can achieve 100% accuracy, but for any test, it seems very difficult. And now we increase this gamma, and these seen anchors can achieve 100% on test data. But for unseen one, it still stays on very low accuracy. And we also found that at this stage, the result of 3 and 4 is not equal to 4 and 3. So we know that the network length function, but it does not have any symmetric rule. And we continue to increase gamma. And for the CN anchors, it still can have a good generalization. But now take a very careful look. We found that the solution of 3 and 4 equals to the solution of 4 and 3. So although it doesn't have generalization on uncertain anchor pairs, but it learns symmetry rules. And if we further continuously increase the gamma, we found that both for CN anchors or unseen anchors, it can achieve almost 100% accuracy. So indeed, yes, we can. We can very carefully tune this gamma and design the experiments to let the neural network remember the data by each way. Next, we will study why initialization matters. We found that initialization can significantly affect the reasoning ability of transformer network. And we have this question very naturally, why initialization matters. We found that a key reason is the phenomenon of condensation. And we have shown in the previous lecture that if we use large initialization, the network learns the data with quite a fluctuated curve. In this example, these blue data points are training data, and these red curves are learned by neural network with large initialization. Definitely, in this case, neural network usually does not generalize well. And if we study its weight evolution during the training, we found that. So here, each dot is one neuron here, and its x value is W and its y value is B. So there's blue lines here, blue curves here, indicates the training trajectory during the whole training. And we found that in this, with this large initialization, almost do not shift too much. So it's very close to or very similar to a linear model. But if we decrease the initialization with small initialization for parameters, we found that the network can fit the data with quite flat curve. And similarly, this is the evolution of parameters during the training. Each dot here is one neuron, indicates one W and one B. And similarly, X indicates W and Y indicates bias. So now let's take a look for the first. After 100 epoch training, neurons will evolve into one direction, and it's equivalent to one neuron. But one neuron is not good enough to fit in the data, so you will have another direction, but still not good enough. So you have more and more direction until you can fit in the data. So we gradually increase the complexity. So one direction is important. For this renew activation function, we know that if you have a positive constant inside this function, you can pull it outside. This is the homogeneity property. And if two neurons that have the same direction, we can combine these two neurons into one neuron. So that is the cartoon picture we have shown many times, that if we use a small initialization after training, neurons in the same layer will get clustered. For example, in this case, the first two neurons will have the same weight, and last three neurons have same weight. So it's equivalent to have a neural network with only two neurons. Then its complexity is quite small. We can adopt the traditional complexity theory to understand why it can still generalize well, although the number of parameters is very large. So for small initialization, you will use a flat curve to fit data, but for large initialization, you will use a quite fluctuated curve. And initialization is often called magic during the training. Why is called magic? We have mentioned a small initialization or large initialization, but how small and how large? For example, when we are training a large language model, we usually don't directly test everything on very large language model, but we do it on a quite a small one and then scale it up. So, for example, we found initial variance Gaussian distribution are very useful, a very good performance for a network. And now we change or decrease or use a smaller network. This number does not work anymore. Or we use scale it to a very large network. This number does not work either. Why? Because we found that the key thing is not the variance, but this initialization rate gamma here. We found that for network with different size, if this gamma stays the same, the network will have similar behavior. Now let's examine the condensation in a transformer with the small initialization. The network of transformer is quite complicated compared with this only fully connected structure. But never mind, we will take a look at one parameter. For example, this Q. This Q equals to the product of X and W. This X is the input. And each column of X will have inner product with this input and have output. So each column can be regarded as the weight of a neuron. And we can examine the similarity between neurons, so we can examine the cosine similarity between columns of this weight matrix. So consider a very extreme case. If all columns are same, well then, that means all the output are the same. So this is equivalent to very few effective neurons, and at extreme case, is only one neuron. Now let's examine this cosine similarity. So we can see that if you use small initialization, these are all neuron index or column index. There are many columns, they are highly similar. So they can almost be equivalent or compressed into one. So originally we have a very large weight matrix and the network is very complex. But now, after training, it's equivalent to a very small weight matrix. But for large initialization, there is no condensation. And this condensation is quite common for small initialization. This is the scale of initialization. And we found that as the initialization rate gamma increase or the variance decrease, we can see that for different layers, the network always have this condensation. And we also found that if we constrain the complexity by initialization, the word embedding is also very regular. For small initialization, these tokens are embedded in a very regular way. But for large initialization, it's embedded quite random. So now we can have a very simple conclusion here. If you have small initialization, you have very condensed, very much condensed. And neural network will use low complexity as possible to feed the data, because increase the complexity requires more training. So the neural network will try to remember as less as it can, so you only remember 4 functions. If we only remember 4 functions, then it should also remember this composite rule, then you will generalize on inference. But if we use large initialization, it only has very slight condense, and the complexity is large. It will be easy for it to fit these 10 symmetric mappings, and then you will generalize on symmetric mappings. And if you have very large initialization, there is no condense at all. and the complexity is very, very large, and it can easily fit all mappings, all data. Then it does not have any generalization on any data. And once we use this small initialization, we figure out it might learn the primitive level function and then use this composition. So we need to verify it. Does the network learn each anchor mapping? To do this, we use a mask strategy. We call it remove one anchor during the forward process. So in this case, we have this X as key and the first anchor token and the second anchor token. And we also have some noise to increase the robustness of the network. So we will mask all the information from this second anchor for trained network. So the final output will exclude the information of A2. So basically, this result should be the key token with this first anchor function. And now let's take a look of this representation. We found that if the result is the same, these representations are very similar, meaning it has its intrinsic rule to remember each data. So, for example, this are the cosine similarity of this output. And each block, inside each block, their output is the same, but different blocks, their result are different. So let's take a look at this case. So in this column, we compute the cosine similarity with this result x equals to 54 and a1 equals to the first anchor. Here we use a for 1 for in case some misunderstanding of this as a number and this is also as a number. So we use later to indicate an anchor here. So we can see that all these 4 cases, their result are all 59, and their cosine similarity are very, very high, almost equals to 1. But okay, for another block, their result is 60. These two, inside the block, they have high similarity, but between the block, they have low similarity, meaning the network learns one representation for one result. So this helps us to validate that the neural network highly possibly learns each anchor mapping. And we can also make a small prediction. So if the neural network really learns the symmetry function, and once we only keep the symmetry, the network should not have any difference at learning. But if the neural network learns the inferential solution, meaning the primitive level function, and if we change the data set, it might change it, although it keeps symmetry. For example, here we have these 4 elementary functions, and these are their composite function. And if we randomly change some, for example, this red one, we change it to non-compositional rule. So there should be, for symmetry, they still keep a symmetry. So for symmetry, the solution, its complexity does not change. But for inferential complexity, its complexity definitely increase. So we define this inferential complexity as the number of the symmetry pair changed. So in this case, there are symmetry pair changed. So this IC equals to 3. For small initialization, you will have very serious condense, and you will use low complexity as possible. And if we increase this inferential complexity, it will require more steps to learn. But for large initialization, it has very slight condensation and large complexity. It always learns these 10 symmetric mappings for any inferential complexity. So it will have similar steps for any inferential complexity. Now let's take a look at the result. For small initialization, it will learn inferential solution. And once we increase this inferential complexity from 0 to 5, these training steps increase significantly. But for large initialization, it almost does not change. So this verifies our prediction. And we know that complexity restriction is the key. So we can find some other technique to restrict the complexity. For example, the weight decay. We found that large weight decay or large learning rate with certain range, it can facilitate condensation. So you will least inferential solution. So this is the accuracy of inferential solution of our example. If we increase the learning rate or increase the weight decay penalty coefficient, this accuracy increase indicates it will turn to inferential solution. And we can verify our result in more experiments. Here is a very interesting phenomenon. In this paper, they call it failure mode. What's this result? They train a diffusion model and use 3 index to indicate 3 properties. For example, if the first number is 0, indicates its shape is round. If the first number is 1, indicates it's a triangle. And for the second number, for the second number, if the second number is 0, this indicates this is a large shape. Otherwise, it's a small shape. And for the last one, if the last number is 1, indicates it's blue. Otherwise, it's red. So each one indicates one property. And this combination will have the final picture of composition. And they found that if we only use 4 examples to train the model, this black case, to train the diffusion model, it seems it's very difficult for network to generate other patterns. Of course, during the training, you will have some numbers very close to this 0 to indicate, to generate the same picture. So it has a lot of training data. But they found that it seems the neural network can never learn these composition rules. For example, for this 0, 1, 1, it should generate this small shape circle with blue, but it learns with this result. We found this is a composition task, so if we want to achieve successfully, we only need to decrease the initialization scale or increase this gamma. And we found that if we increase this gamma, the result will be very similar to the target. So we can solve this failure mode very easily. This is for some other more realistic data set. Small initialization can achieve better result. And for addition task, we found very interestingly, if you use a common setting, the test accuracy is very, very low, almost 0%. But if you use small initialization or large weight decay, this test accuracy can be achieved 100% very easily. And that is a very interesting task. So we initialize the model at memorization regime, and we change the data size. So if the data size is small, we found that the neural network memorizes the data, and the accuracy for inferential solution is low. And if we increase the number of data, the neural network needs more training steps to remember the data, definitely, because there are more data, more complexity. And after some critical value, we found that the network suddenly use much smaller training steps. How and why? Okay, the explanation can be as following. If the number of data sets is too large, then the network cannot remember the data anymore. So it has to find some basic rules. So once it found the basic rules, the things it needs to remember is much less. So it requires much less steps to remember the data. And it still can achieve very high accuracy. So actually this gives us some hint. If we are going to assign some tasks to students, we should never assign too few. Otherwise, it just remember it or just do it randomly. They can use some very stupid way. They can solve it. But if we assign too many tasks for the student, it has to find the basic rule. And once it finds the basic rule, it can use much less time and also still have a very good performance. And we also applied our small initialization and large weight decay to a memory cubic large language model with 0.8 billion model parameters and 100 billion data tokens. And we found that the average score for benchmarks increased by 7.5%. This is equivalent to the scale of 28 of original network size. And very interestingly, the math and professional tests are more significant. For example, for GSM 8K, GSM 8K, increment is increased very significantly from large initialization or common initialization to small initialization. That is very consistent with our expectation. So until here, we have almost ended our small series lecture. So this reasoning is very closely related to this initialization. And that is also an implicit bias we studied in the fully connected networks. We found that with this frequency principle or condensation induced by initialization or dropout or other technique, the neural network will use low complexity simple function to fit the data to achieve good generalization. And finally, let's think again, what is deep learning? So we can start from this linear regression. We want to fit data points with a linear function, but if data points are not linear, we should use some nonlinear activation to change this linear form. So we have these neural networks, and it's so powerful. Now, why bother? We need a theory. One side of the theory can help us to improve our algorithm. On the other side, it can also help us understand the good and bad side of the algorithm and can help us avoiding wasting energy. For example, if we know the first law of thermodynamics, conservation of energy, we can avoid energy to build a perpetual motion machine of the first kind, or waste the energy to translate copper into gold. But once we know that wood carbon can be transformed into diamond, we can build machines to construct such conditions. So now the artificial diamond is very common. So what is a good theory or bad one? In this area, that there are so many papers, I think that there are some basic criteria. That is, you should reveal some interesting phenomenon or theoretical questions. And it also should be simple enough for analysis, yet complex enough to illuminate the real issues. and its prediction should be verified by experiments. And there are some advanced criteria. It should be able to lead to more interesting phenomena or theories, or guide our designing for algorithms. And in this lecture series, we cover the frequency, some introduction of phenomena, and frequency principle or spectrum bias, or neuron condensation or called neural alignment. And finally, we also study the reasoning of transformer-based language model. And we also propose this anchor function to study it with less computation resource. And if you are Chinese, you can read our lecture notes in GitHub. And we have many papers on my personal website. Welcome to contact if you are interested in our works. And thank you.